Okay, you guys, this is chapter 6, sections 1 through 4. It's on light and matter. And we're going to go through this pretty quickly, and it's going to be the extent of it. So, light, it behaves like two things. It behaves like both a wave and a particle. The particle part is kind of new to you guys, but last year we talked about it a little bit during flame testing. So, some things that you should be familiar with the wave that I'm not going to cover hugely are wavelength, amplitude, and what the two things mean. So your wavelength is the length from one crest or one peak to the other, okay? Your amplitude is from the midpoint, okay, to the top or to the bottom. If you have a wavelength like this that is short, you are going to have a higher frequency. Frequency being the amount of time it takes to pass through a certain point, how many times it passes a certain point. Is it more frequent or less frequent? Okay. Here we have a high amplitude. Here we have a low amplitude. And we call something that we use to turn up the volume on things an amplifier, because the louder you turn something up, the more it is amplified. In this picture down here, we have the light behaving like particles, and you've got some radiant energy, which is like from the sun, hitting a piece of metal, and it's shooting off electrons, okay? So light as waves, we have this funky little equation right here, okay, where c is for the speed of light. Lambda, this is the Greek symbol lambda, is for wavelength. And this, which looks like a V, is not a V. It is actually the Greek letter nu. It's the lowercase nu in Greek. That is for frequency. Okay, so we can do some calculations based on the speed of light, all right, with this equation. I want to point out over here that the amount of visible light that we see, I mean, if you take a look at how big this spectrum is, the electromagnetic spectrum, this little tiny piece right here is all we actually see, okay? All right, so I blew this up a little bit bigger for you for this reason. The question at the top is, why do different forms of electromagnetic radiation have different properties? And it's because of their wavelength, okay? Let's take a look at this. Down here, we have a very large wavelength. Radio frequency, radio waves are all around us, okay? And then we move on to microwaves, which are a little bit smaller, and then we move on to infrared rays, and then we have our visible light, okay? And that's what we see. Now, when we start to talk about ultraviolet and X-rays and gamma rays, these are all rays that we protect ourselves from, okay? We use sunscreen for this, to protect ourselves from this. We use lead aprons to protect ourselves from these. And this, we use a lot more protective gear, okay, than even lead aprons, because these waves, which are much shorter and therefore have a much higher frequency, are much more dangerous to us, okay? They're much more penetrating, much more dangerous. Notice here it says that frequency is increasing, okay? So if we were going to draw wavelengths of these wavelengths would be, you know, big wavelengths. And down here, we would have these little tiny wavelengths, okay? All right, here we got a picture of a guy running up some stairs because it says light as particles, and it says Max Planck, energy can only be emitted or absorbed in chunks. He called these chunks quantum. And the reason there's a guy running up the stairs is because if you think about it, you can't go up half a stair, okay? You can only go